Alright, okay, welcome everyone to the stream. We're gonna be doing predicates and proofs today, and it's interesting because the more I look at the questions on this stream, or rather for this stream today, it actually links a lot to the future ideas on different concepts which will require predicates to be defined properly. So we are going to do just that. And we'll start with the first question on relations. Now, we will talk about relations eventually, but for now, let's just start with the first question. And we have a bunch of propositions which we need to write in terms of symbols. And what symbols are we talking about this time around? We're going to be talking about the universal quantifier and the existential quantifier. Right? So the idea being that this statement doesn't really make a lot of sense. What does it mean? We are all tempted to solve it as x equals to 3. However, this itself as a proposition makes no sense. Is it true? Is it false? We don't know. But if we were to consider a quantifier, say any integer x, or some integer x, now this statement has a truth value. In the bottom case, it's true because we can choose x equals to, well, 3. That's something we're all familiar with even at the primary school level. And the proposition above is not going to be true because, well, we can find a counterexample. Well, 0 is an integer, and yet 0 plus 2 is 2 is certainly not equals to 5. So predicates help scope our question so that we know what we're talking about, so that we can derive whether it's actually true or false. So that's what we want to do today. We are going to consider these propositions for any x in A, well, awkward, x are x for any element x of A. And we want to represent this using symbols. So the idea here is to first consider what we're talking about. Let's first scope what we're talking about and then write out the statement proper, right? So since we're talking about any element x of A, we'll phrase this as for any element x of A, x are x, whatever this means. And of course, this will be eventually talked about. This is called reflexivity. So for any x of A, any element x of A, x is related to x. We usually represent x being an element of A using the notation x in A. So the way to convey this idea is for any x in A, x is related to x. That's how we translate this proposition in English into symbols. So we have another concept, it's called symmetry. And it says this: for all elements x, y of A such, well, oops, awkward, of A such that x is related to y, one must have y related to x. And we need to represent this using symbols. So here's our symbols once again. So since we're considering any element x and y of A, it will be xy in A, and for any element. And we have this little property over here, such that something, and then one must have y related to x. So this is a situation where we care about the elements xy of A that satisfy xry. But could it be entirely possible that x is not related to y? Well, whatever this means, it's entirely possible. But do we care about that? over here we are only concerned about the elements x and y that satisfy this property. If they don't satisfy this property, we don't care. Anything can happen. And since we do not really care about about the situation when x is not related to y, we will use this symbol. XRY implies YRX. This is very much confused between this expression and this expression. A lot of people mix the two up, and roughly speaking, the difference is that in this case, in the first case, if x related to y is false, no one cares. Oops. No one cares. But if, on the other hand, for the other situation, if XRY is false, we will declare this expression to be false. And that's the big difference between the implication from the conjunction. So that's our solution. And finally, for part C, we have this concept called anti-symmetry. And it says this: no distinct elements x, y of A satisfy both XRY and YRX. And if you've already learned anti-symmetry, of course you can just copy and paste the definition. But if we do not know anything about anti-symmetry and we need to interpret this statement, then it's a little tricky. How exactly do we go about it? The sort of strategy that I would go at it is, what's the opposite of no distinct elements? The opposite of no distinct elements is, well, some distinct elements. And so I'm going to take the negation of some distinct elements. So it's almost like the negation of some distinct elements such that blah blah blah. And to say some distinct elements assumes firstly we have elements that are distinct. Right? We have elements, and these elements must be distinct. So this time, if they are not distinct, we actually care. In the negation, everything on the inside, we do actually care. Right? We do actually care about there being distinct elements that violate some condition. So here's how I might go about it. In the negation of some distinct elements x, y of A, that, well, the negation of there are some distinct elements of A, x and y of A is such that x are y and y are x. And the way I would think about this is, well, if there are some distinct elements, that is the same thing as saying, I think we can use triple arrows here. There exist elements x and y of A such that x and y are distinct and x are y, and y are x. This bit over here can be written as x are y and y are x. And there are a few ways to sort of simplify this. In fact, we can try to push the negation symbol inside and see what we're going to get. So let's try that out, and when we push the negation symbol, any instance of there exists becomes for all. So we will get for all x, y in A, the negation of the conjunction. And I'm going to write the conjunction this way because there's a little trick which I have up my sleeve. So we can write the conjunction in this way. And then we can push in the negation because if we recall correctly, using De Morgan's law, we can push the negation symbol to get negation of P or negation of Q. So this is going to be pushed in to get this particular negation, and I'm going to do it this way. It's a little sneaky, but I'm going to do it this way. So negation of x not equals to y, or negation of x are y and y are x. And instead of writing negation of x not equals to y, I'm going to write this as, well, x equals to y. The opposite of x not equals to y is x equals to y. And you might be wondering, wait a minute, what sneaky things am I up to? Well, here's what I'm up to. I'm going to write this as the negation of P or Q. And the astute among you might realize that should sound very suspicious at this point in time, because the negation of P or Q can be written as P implies Q. And I want to write this as for all x, y in A, x are y and y are x implies x equals to y. In fact, when we do get on the topic of relations and partial orders, this is indeed the definition of antisymmetry. And that is sort of how we can actually formulate antisymmetry, because someone else, instead of using this no distinct elements language, decides to phrase it as if x, y are elements of A that satisfy x are y and y are x, then x and y must be equal. In fact, if we look at what we've written down, this is precisely this statement. Because if x and y are elements of A, so in other words, for any element xy of A that satisfy this property, alright, so let me highlight that. For any element x and y in A that satisfy this property, in other words, if they don't satisfy the property, nobody cares. No one cares at all. Then x and y must be equal. And that is actually precisely the statement in English that's now converted into symbols. So that is actually another question. Alright, ironically this is actually the second question. This is question 1. Ironically this is actually our second question, but it's all sort of connected to one another. So there's that. For our third question, we need to write some of the symbols symbolically. So firstly, there is no largest natural number. So what does that mean? Well, it means that it's the opposite of there is a largest natural number, right? So here's how I might phrase it. Is the negation of there is a largest natural number. And how do we convey this idea of largest natural number? Well, a natural number is the largest if, well, largest means what? Means bigger than any other number. So largest natural number, roughly speaking, means for any natural number We call this largest natural number, say, m, and we'll call any natural number n. If it's the largest, then n has to be smaller than or equals to m. Now, we're not saying whether this proposition is true or false, we're just writing out the statement, and whether it's true or not remains to be seen. So we're going to write it this way. So the negation of there is a largest natural number. Now, there is a natural number such that for any natural number, any other natural number, n is less than or equals to m. Well, capital M. And this might be a bit difficult to work with. We might want to push in the negation symbols. So the negation interacts with the exists to give a for all. The negation interacts with the for all to give a there exists. And the negation interacts with the less than or equals to more than. So the idea being that a less than or equals to b means a equals to b or a less than b. So the negation is the negation of that, which is when a is more than b. So that is the question, and we are asked, well, we can try to prove this statement. Is this true or false? There is no largest natural number. Well, if we start with the number 1, what number is bigger than that? 2. And what number is bigger than that? 3. Bigger than that? 4, 5, 6, 7, 8. In other words, we can fix any number we want. Is there a number that will be bigger than this number? Yes, right? We can choose the witness n equals to m plus 1. Then we can conclude that n equals to m plus 1 being bigger to m. And therefore, the statement is, the proposition is true. Of course, we're working in natural numbers here, so I know some people are really excited about other kinds of objects, and there are interesting ideas out there. Alright, next question is gonna be, between any two distinct rational numbers, there exists another one. So, between any two distinct rational numbers, there exists another one. And we usually use the symbol Q to represent the set of rational numbers. So let's write this using symbols and go ahead and try to prove it. Between any two distinct rational numbers. So for any rational numbers, or in this case, the between any is going to give me a for any kind of vibes there. So it's for any x and y in the rational numbers. Well, if they are the same, no one cares. But if they are distinct, we want there to be another rational number in between them. So, we're going to use the implication in this case. Right? X not equals to y will imply that there is another one. There is another one. Well, there is another rational number. With what property? That lies between the two distinct rational numbers. Now, since x and y are distinct, we must have x being less than y, or y being less than x. And here's a brief picture. We'll definitely look at more of this in my future videos on analysis. So if you're looking forward to that, stay tuned for that. Then the idea is there should be some other guy z in between these two rational numbers. However, we do need to distinguish between the two cases because we actually don't know which one's the one. We don't know whether x is bigger than y or y is bigger than x. So we need to distinguish them. So there exists a z in Q such that either it lies in between x and y in the sense that x is smaller than y, or it will lie in between y and x in the sense that y is smaller than x. And well, here's an interesting question. Is that true or false? Well, based on our picture, it sort of makes sense that it should be true, right? So let's go ahead to prove it. Fix x, y in the rational numbers, and suppose x is not equals to y. And we actually need to check two cases, right? We need to check whether x is smaller than y or x is bigger than y. Then suppose, well, either x is smaller than y or x is bigger than y. So for case A, suppose x is smaller than y, then the idea is to sort of take the rational number, as we've seen over here. We try to take the guy in the middle. So what's in the middle of x and y? Well, the midway point, right? So choose z as the midway point of x plus y. Now, since x is a rational number and y is a rational number, the sum is a rational number. And when you multiply two rational numbers together, the whole thing is going to be rational. So z is going to be a rational number. And furthermore, we have the property that, let's check that z actually lies in between x and y. So x plus y over 2, this is your z. Since x is smaller than y, x plus y will be smaller than y plus y. And since y is bigger than x plus y will be bigger than x plus x over 2. On the left side, we have 2x divided by 2. On the right side, we have 2y divided by 2. And therefore, we do check that z does lie in between x and y. Feel free to check the second case for yourself. I'm gonna just leave it here for you to check. Because why not, right? Let's do a little bit of participation here and there. Alright. So we have those questions. Now we have question 4. And this question is going to be a question on how to do negations. So we have a bunch of propositions and we need to negate all of them. So here is the first proposition. For any x in R, there exists y in R with the property that y equals to x squared. And we need to negate this. So how do we negate this statement? We will negate this statement by putting a negation symbol and trying our best to push it in as much as we can so we can tease out even more information about what's going on here. So let's negate. Now we need to push in the negation symbol. So we can push in the negation on the for all to get a there exists. We can put in the negation of the there exists to get a for all. And we can consider the negation of y equals to x squared. And well, the negation of y equals to x squared is actually y is not equals to x squared. So that is the question. And we might want to check whether this is true or false. Is this true or false? In other words, is the original guy true or false? Well, for any x, there is a y in R such that y equals x squared. That sounds about right. Yeah, that kind of sounds about right. Yeah, that sounds about right. So let's circle through and let's go ahead and prove it. So we'll first fix any x in R. And we can consider y equals to x times x, that's x squared. Since you multiply two real numbers, you can get a real number. This guy's gonna be a real number. Then, by definition, y equals to x squared. So we need to choose the y and show that the y and the x agree in that last bit over there. So therefore it's true. And we're gonna flip some items here. For any y in R that exists x in R, such that y equals to x squared. These two statements look very, very, very similar. But are they really the same? Well, we're just gonna put true and false here. Let's first negate it and see what we get. Let's negate this statement. And we can follow the exact same rules as before to obtain a very similar expression. But now this raises a question, is this actually true or false? Is the original guy true or false? It may be true, it may be false, we don't know, we sort of need a proof, but the idea here is for any output y, can we find an input such that y equals x squared? But what if the output is negative? Then, as far as real numbers are concerned, let's not go to complex numbers here. As far as real numbers are concerned, we can't square a real number to get a negative number. And so, let's show that the original guy is false and prove that the negation is true. So how do we show that the negation is true? We will choose y equals to -1. Then, for any x in R, what do we know about y? Well, x squared is the square of a real number. In the square of a real number, we've sort of briefly learned it in time past. It's always non-negative. So it's always non-negative. But if it's non-negative, then it has to be strictly bigger than -1. And if it's strictly bigger than -1, then it is strictly bigger than y. Therefore, x squared is strictly bigger than y, which implies that x squared cannot equals to y. So we prove that the original statement is false by proving that its negation is true. Let's go on to the next one. Next one's a little bit long. Looks a bit long, but we'll do it. For any x1, x2, y1, y2 in R, y1 equals to x1 squared and y2 equals to x2 squared. And x1 not equals to x2 will imply that y1 not equals to y2. We'll eventually ask if this is true or false. But for now, before we even try to negate this statement, and we will need to negate this statement eventually, we first want to put some brackets here. Because there is a convention that says, based on our hierarchy of operators, of our connectors, hierarchy of connectors, then we should place the brackets over here, because conjunction has higher priority over implication. So let's go ahead and negate everything. This looks kind of painful, but I think we can do it. So we negate the for all, right? In the back of my mind, we're negating the for all, and I'm lazy, so I'm just gonna copy and paste this, because why not, right? There we go, look at that! What the heck? I always like to say, and this is pretty much new in the channel, but true in life, math people are pretty lazy and we are pretty crazy. So that's the negation. So what happens when we push the negation symbol in? We're gonna get there exists x1, x2, y1, y2 in R. with the property that we'll get a negation of a implication. And I'm gonna just copy and paste this implication. Because, once again, I'm lazy. And I don't intend to stop being lazy. Unless I need to, like that. Well, that's awkward and embarrassing. Let's try that again. Almost there. Look at that. And done. So yes, math people are really, really lazy. Negation of an implication. As we recall, the negation of P implies Q. It's very tempting to just push the negation symbol in, right? But based on truth tables, and we can demonstrate this, the negation of an implication is P and not Q. Let me very quickly verify this fact over here. So this is P and Q. P implies Q. P and not Q. Well, we have quite a few things to check, right? Let's very quickly verify this and then we can move on with our lives. So let's negate this guy. Let's find negation of Q, P and negation of Q. We're going to make sure that these two guys really are equal to one another. So let's check. This to be trues. And everything else will be falses. So in the first implication, we're going to get true implies true is true. True implies false will be false. And false implies anything is going to be true. If we negate all of that, we're just going to get this true over here. The negation of Q is going to be false if Q is true and true if Q is false. And finally, we're going to take the intersection of P and not Q. So when P is true and Q is false, P and not Q is false. And when P is true and not Q is true, we get truth there. In every other instance, will get us false. And we can indeed check that these two columns do agree with one another. Also say that the negation of the implication is P and not Q. So P and not Q. Because not of not equals is equals. And now the question that we should ask is this true or false? The original statement says that for any x1, x2, y1, y2, if y1 equals to x1 squared and y2 equals to x2 squared, and x1 and x2 are not equal to each other, then y1 cannot equal to y2. So in other words, if the inputs are different, the squares must be different. But when we consider a parabola, once again, consider a parabola, we could have the same output given different inputs. Say 1 and -1. They're going to give us, well, that's very badly drawn. Let's try that again. We're going to get 1 over here. We're actually going to get 1. And what that means, therefore, is that if that's going to give us 1, we found a counter example. In fact, the negation is going to be true, right? So it's going to be false. And let's prove our assertion. We're going to choose two inputs, right? So we'll choose, because there exists requires us to choose. If we're trying to prove a there exists statement, we need to come up with the witness. So choose x1 equals to 1, x2 equals to -1, y1 equals to 1, and y2 equals to 1. What does that give us? Then y1, let's check if it equals to x1 squared, where y1 is 1, x1 is 1, so x1 squared is 1, where 1 squared and these two do indeed work out. y2 and x2 squared, let's check it out again. y2 is 1, x2 squared is minus 1 squared, and 1 does indeed equal to negative 1 all squared. And that's part 2. We've got two more things to check. x1 and x2. x1 is 1, x2 is negative 1, and these items do not agree with one another. So x1 is not equal to x2 is a true statement. Finally, y1 equals to 1, y2 equals to 1, and the two agree. Therefore, it's true. So we found a witness such that all of these guys are true. Therefore, the negation is true. And the original is, well, false. Alright. Now part D is going to be very similar and it's going to be very long, but we will do it. We will do it even though it's tedious. So we need to consider this expression, very similar to the previous one. And we need to ask whether this guy is true or false. So let's work hard to negate the statement once again using very similar techniques. In fact, it's literally the exact same thing except that we've swapped some symbols a bit. So instead of for all, it becomes there exists. And once again, the negation of an implication is, well, the negation of P and Q. The negation of P implies Q is P and not Q. Not Q is going to be not equals, right? So, yeah. And this time, we probably would think it's true because the question sort of indicates that. But we still need to prove it. So let's go ahead and try to prove that it's true. And again, what this tells us is that if the outputs are different, then the inputs must be different. Now, if the outputs are same, it doesn't mean that inputs are same. That's what we actually saw just now, right? Just because the inputs are the same, the inputs are different, does not mean that the outputs are different. However, we're now making a claim that the outputs being different will result in the inputs being different. So let's prove it. And we will fix x1, x2, y1, y2 in the real numbers. We will suppose that y1 equals to x1 squared and y2 equals to x2 squared and y1 is not equals to y2. So what does that tell us? Then it tells us that x1 squared is not equals to x2 squared. So what's our goal? Our goal is to show that x1 is not equals to x2. This is our goal. How do we get to the goal? It's quite difficult to work with square roots because it's not entirely obvious what's going to happen. But we do know if we take two numbers that are equal to each other, then the squares will be equal to each other. That's going to happen for us. So we don't know a lot about two numbers being not equal, but we know a lot about things. We know a lot about numbers being equal to one another. So the way we're going to go about it is this thing called proof by contradiction. Right? So we'll suppose the negation is true. So the negation of this guy is x1 equals to x2. Oops. So we will suppose for contradiction that x1 equals to x2 And when we square the two numbers, then x1 squared equals to x2 squared. However, this will contradict this assertion, contradiction. So to formalize that, let me just draw that in dotted lines. And to formalize that, we'll say which contradicts x1 squared not equals to x2 squared. And that is how we prove by contradiction, which means that the conclusion is, therefore, x1, because we've assumed that x1 equals x2 and arrived at a contradiction, we must conclude that negation is true. So we use a contradiction proof whenever it's easier and we have more tools to work with. That is how we use a contradiction proof. It's not, oh, I see a question type and I'm going to use this proof technique. It's more of what tools do we have at our disposal and how can we make use of that. And it takes time and practice, and it is what it is. So it is something that can be mastered and we can get better at it. So yeah, it's something that with enough practice anyone can do. Let's look at a few more examples. So for any x in R, we want to, well, here's the statement that exists, well, for any x in R, something will happen, right? So if there exists y in R with the property that y equals to x squared, then we can conclude that x is bigger than or equal to 0. And while we're at it, I'm going to just write the statement for f as well. Y in R, there exists x in R, such that y equals x squared, implies that y is positive. So we need to prove these two statements, or at least we first need to negate them. Let's negate them. Oops. So let's negate these statements. Once again, the negation of a for all is there exists. And the negation of an implication is the negation of the first guy and, well, is the first guy, sorry, is P and not Q, right? So we can sort of simplify this not Q business over here. Not more than equals to is, well, less than. So that's fine. That's totally acceptable and that's totally allowed over there. So that's one, and we can go ahead and check the other one as well. So there exists y in R with the property that if there exists x in R such that y equals x squared and y being less than 0. So we can check these properties. Now, once again, we want to ask the question, are they true or false? Today, are they true or false? Well, what do these statements actually say? So these statements tell us that for the first part, whenever I can find a y such that y equals to x squared, then x must be non-negative. But, well, I could find a negative number like -1. If I square it, that's 1, and there's that, right? So in fact, it's gonna be false, and we're gonna choose. We're gonna prove it. Since it's an existence proof, we need to choose x in R. Or we need to choose x equals to, say, -1. That will help us. And we need to verify the remaining statements. We need to check that there exists y in R such that y equals x squared is true. Well, this statement is true, right? Because since y equals to 1 satisfies, well, y equals 1 is a real number, satisfies, let's be precise here, 1, well, y equals to 1 and -1, oops, and -1 squared equals to x squared. Since y equals 1 satisfies this, the statement there exists y in R such that y equals x squared is true. And on the other hand, we have that also x equals to -1 is negative. Right, that it will be this bit over here. So we found a witness such that the two things are true, such that the statement inside is true. Therefore, the negation is true, and the original is gonna be false. And we might expect that the last guy is true, but let's see what it means. It says that for any y in R, if we can find if for any y in the real numbers, if we can find a real number such as y equals to x squared, then y will be bigger than 0. Y will be non-negative, and that's true, right? That's true. So let's check that out. Suppose, let's fix y in R, and we'll suppose that this thing is true. Suppose there exists x in R such that y equals to x squared. Then y equals to x squared, as we've discussed many times. X squared, if x is if x is a real number, then x squared has to be non-negative. And that is precisely the statement that we have shown. Therefore, the original is true. Alright. Now we have a few more propositions we can try to negate and do all that good stuff. So let's go ahead and attempt those. Let's consider this one. We want to write propositionally the statement that an integer d divides an integer n if and only if n is the product of d with some integer. And this looks really long and convoluted, but we can try to break down this expression here. So the idea is an integer d divides an integer n precisely when, if and only if, n is the product of d with some integer. Now what that tells us is that, well, this is going to be a sort of a description for any n and for any d. So we will say that d divides n, and this may or may not be true for the integers, but in principle it could work with anything. So we're gonna write it this way. For any d and n integers, we say that d divides an integer n, and we will note this in this question. Just for this question, we're going to note it by divides dn. So we'll say that divides dn if and only if something. Well, n is the product of d with some integer. Which integer is it? We don't know. As long as we have one integer, we want n to be a product of d with some integer, we'll call that d dividing n. So we need it to be n equals to d times some integer. And since we only need some integer, not every single integer, there exists some integer k, the property that n is the product of d and k. And that's how we write this symbolically. Let's look at another question pertaining negations and provings and all that good stuff. So we'll let d equals to the set 1, 3, 5, 7, 9, 11, 13. This is actually the odd numbers that are less than 14, I guess. And e is going to be the set containing 0, 2, 4, and 6. And we are going to look at, we're going to look at some propositions, and we want to consider the negations and see whether they're true or false. So let's see. For any x in D, there exists y in E with the property that y is smaller than x. That's one. And we'll slowly go down the list of the different propositions we want to negate. So let's check out what's its negation. We want to find its negation and then ask the question whether it's true or false, and we'll give a proof. So let's write the negation. Once again, we push in the negation symbol, so any time the negation interacts with a for all, it becomes there exists. Exists becomes for all. And the negation of less than is more than or equals to. So that is going to be our negation. Now, is this true or not? Is it true that no matter which D we pick, we can find a y in E such that y is smaller than x? Well, yeah, I think there is one actually. So let's check this out. So in fact, we have a very convenient example here. So let's fix any of these numbers, 1, 3, 5, 7, 9. Choose whichever you want, and then we'll choose y equals to 0, which belongs to E. Then any number in D, actually x, well, y is going to be 0, is actually going to be strictly smaller than the smallest number in D. And any number in D is going to be bigger than or equal to 1, but 1 is bigger strictly than 0, which is equal to y. And that's our proof. Next one is, there exists y in E with the property that for any x in D, y is less than x. Let's negate this statement. We're going to find the negation of this statement and then check whether this guy is true or false. So the negation of the statement is that no matter which y we choose, right, we can find an x in D with the property that y is, instead of smaller than x, is going to be bigger than or equal to x. I should have done this in a different color. There we go. So the real question that remains is this true or false? Well, do we have a number that is strictly smaller than every single number in D? Surprisingly, the answer is true, right? So we need to prove it. And how do we prove it? We'll choose y equals to 0. Then, for any x in D, x is always bigger than or equals to 1, which is always, well, bigger than 0, which is y. And therefore, y is smaller than x as required. So in this situation, the for and there exists, both statements are true. It doesn't always have to be true, it doesn't always have to be false. We have to be careful each and every time. The next statement says this. For any x in D, there exists y in E with the property that y plus 1 equals to x. So that is the question. For any x in D, there exists a y in E such that this is true. Let's negate it and check whether it's true or false. To negate it, every for all becomes there exists. And every exists becomes for all. And equals become not equals. And that raises the question, is this statement true or false? And the statement in its original form says, for any item in D, you can find y in E such that y plus 1 equals x. The negation says that you can find some guy in D such that no matter who you choose in E, y plus 1 will never equal to x. I think the negation is true this time around. Because we can choose a really large number in D. Say x equals to 13. I think we should be precise here and say this belongs to E. So we choose x equals 13, which belongs to D. Then, for any y in E, we'll notice that y is not more than 6. Right? Y is not more than 6, which means that y plus 1 is not more than 7. But 7 is really small compared to 13. And therefore, y plus 1 can never equal to 13. And there we have it. That's a statement that's false. Because we proved that the negation is true. Let's put the set here again for our reference. And we're going to write out this statement here. So for any x in D, x less than 6 implies there exists y in E with the property that y plus 1 equals to x. Well, we first need to negate this statement. And then we need to check whether it's true or false. So let's do this slowly. Now to negate the statement, we flip the for all to there exists. Let me write that in this color. And to negate an implication is going to be P and not Q. And I'm actually not going to simplify everything right away because it's really unwieldy. So let's go ahead to simplify this one more time. And we can push in the negation symbol one more time over here. So instead of all of that, is going to be a negation of there exists becomes for all, and the negation of a not equals of an equals becomes not equals. So that's sort of the negation over there. And we need to check that is this true or false? Is this statement true or false? I think the original statement is true this time around. And the reason why is because what's going on in my head? Well, wait, I think x in D. Oh, x in D. Okay, we need to be very careful here, right? Because let's check. Did I prove it correctly? Okay, x in D. All right. X in D. So for any x in D, if x is smaller than 6, then we can find y such that y plus 1 equals to 6. Well, I think that's true. I think that's true. So my guess is that it's true and we're going to prove it. So we need to fix x in D and we will make the assumption that x is less than 6. Now if x is more than 6, no one cares. But if x is less than 6, then since x lies in D, we have either x equals to 1 or x equals to 3 or x equals to 5. Well, if x is in D and it's smaller than 6, then it has to be one of these 3 options. And what do? We're going to, in each case, choose y. If x equals to 1, I'm going to choose y equals to 0. If x equals to 3, I'm going to choose y equals to 2. And if x equals to 5, I'm going to choose y equals to 4. Now, what's the idea there, right? Of course, the quick math here is that if y plus 1 equals to x, then y should be equal to x minus 1. So if x equals to 1, I want to choose y equals 0. And it turns out that all of these numbers lie inside E. then in each situation, y plus 1 equals to x, y plus 1 equals to x, and y plus 1 equals to x. So all of these situations, y plus 1 equals to x. So therefore, for any x in D with x less than 6, there does exist y in E with the property that y plus 1 equals to x, which is precisely the statement that we were proving. If x is bigger than 6 or bigger than or equals to 6, no one cares. But if it's less than 6, we can find a guy in Y, we can find a guy in E that satisfies this property. That's the idea. Alright. Let's go ahead and try to do some more proving. So we're gonna do this one over here. I'm gonna call this question 7. So we claim that for any x in real numbers, x squared will be bigger than or equal to 0. There is a very interesting proof involving ideas from real analysis. Well, not really real analysis, but using the properties of real numbers to make this proof. Do let me know in the comment section if you want to see this proof. But there is an interesting proof. Now, a student does attempt this proof, actually. It does attempt this proof. Actually, let me think. I think we might want to go ahead to... Okay, no, let's look at the... Let's go ahead to try to prove this claim, right? So sometimes we can prove it, sometimes it's not as easy. So we are gonna prove this claim, and this is a pretty interesting claim over here, right? So we need to prove that for any x in R, x squared is bigger than or equals to 0. Now, we are actually not assuming we know anything about discriminants. I know some of you guys love to just put discriminants, but strictly speaking, we don't know anything about discriminants as of now. So how do we even start? Well, here's the idea. Fix x as your real number. And since x is a real number, we have exactly one of 3 cases. Right? The first case is that x is positive. The second case is that x is equal to 0. And the third case is that x is negative. Right? So we need to check that for any situation, we will get x squared being bigger than or equal to 0. Let's look at x equals 0. That's actually the easiest case here, because if x equals to 0, then x squared is 0 squared. And 0 times anything is 0. So we're good to go. Now if x is positive, something interesting happens here. X squared is actually a positive term times a positive term. And when you multiply 2 positive terms, you're going to get a positive term. So that works out well, and we didn't even need that much space. That's interesting. Now the last proof is pretty much the most interesting proof I find, and that is the fact that if x is negative, then negative of x is positive. And by A, the square of negative x has to be positive, because we've shown that if a number is positive, its square must be positive. But by algebra, we can actually check that this will equal to x squared. So in the first situation, we get x squared being bigger than 0, which means that the weaker inequality is true. In the second case, we got x squared equals to 0, which means that the weaker inequality is also true. In the third case, we have the strict inequality, which means that the weaker inequality is true as well. And therefore, we can conclude that for any x in R, x squared is bigger than or equal to 0. Now, my favorite part of this proof, and I shared this with my class before, is that by parts A and C, we can prove that 1 is bigger than 0 as follows. Since 1 is not equals to 0, by A and C, 1 squared is bigger than 0. A and C actually combine to tell us that, this, right? If x is non-zero, then x squared is positive. So if 1 is non-zero, then 1 squared has to be positive, but 1 squared is 1 times anything, well, 1 times itself, so it remains the same. It's just 1. So we therefore, 1 is bigger than 0. Yes, it's a rather long proof as to why 1 is bigger than 0, but that was one of the things that actually fascinated me at the university level. Now, question 8. Here's the claim. The claim is that there exists a real number x with the property that x squared plus 9 equals to 6x. So we could go on a hunt. So let's try to go on a hunt for this x, right? So here's our proof. Well, we need to show that x squared plus 9 equals to 6x, which means that x squared minus 6x plus 9 equals to 0, which means that x minus 3 by completing the square is equal to 0, which means that x minus 3 equals to 0, therefore x equals to 3. And at this point in time, we might think to ourselves, we have the solution, but we didn't actually answer the question. What we have done here is prove the statement. We've actually proved this statement. For any x in R, if it satisfies this equation, then x equals to 3. We've actually not proven the question. We've actually not answered the question. We actually need to give an x such that this equation is true. So this is working. This is actually fair working, except that it's not really a proof. So I'm just gonna dotted line this guy here, and therefore now prove it properly. So we're gonna choose x equals to 3. Then x squared plus 9 is gonna be 3 squared plus 9 is 18. That is equal to 6 times 3, which is 6x. And that's how we prove it. So in principle, if we don't even show any of this work at all, and we could still obtain x equals to 3, we still answer the question and prove the result, and we can get full credit. So that's rather interesting. It's like, wait a minute, I thought we gotta show our working. Well, in a sense, yeah, this is your working. You have to answer the question. So that's the important part. So in the next part, we are going to establish an equivalent formulation. Okay, so what are we gonna do? So here's the question, right? Let's we'll let Pxy be a predicate on a set A. And what exactly do we mean by a predicate? We mean that when we plug in the values, we will get true or false. So for example, x plus 3 equals to 5 is a predicate on, for example, z. Could be other things, but z. So if you plug in an integer, say 0, you're gonna get a false response. The computer is gonna say false. And if you plug in a correct value, it's gonna reply ding ding true. So that's what I mean by a predicate. When you plug in an item from the set, you get a proposition that can be true or false. So we want to prove, and our claim is this. Our claim is that we have two statements that are equivalent to one another. Alright, so let's just copy them down. Right, let's write A and B this way. A is this statement: for any x, y in A, Pxy implies Pyx. And for B, the claim is that for any x, y in A, Pxy and Pyx, or not Pxy and not Pyx. So our claim is that A and B are equivalent to one another. And how do we prove equivalence? You might have watched the linear algebra videos, you might have not, doesn't matter. How do we prove equivalence? We'll need to prove in two directions. So let's go from left to right first. So we'll suppose A is true. That means we're going to suppose this statement for any x, y in A. Pxy implies pyx. If pxy holds, then pyx must hold. Now, we haven't actually used anything from A yet, right? We actually need to prove B. So our goal, what's our goal? Our goal, well, let's first fix xy in A, because it's a for all statement, right? We need to prove B. Okay, so we want to prove B, and for B, it's a for all statement. So we need to fix x, y in A. And what's our goal? Our goal is to show that pxy and pyx, or not pxy and not pyx. This is our goal. So this is a rather lofty goal. It's not exactly an obvious goal, I would say, but we'll have to think about it. So if x and y are items in A, then pxy, since pxy is a predicate on A, if you plug in items from A, this is a proposition. Which means that pxy is either true or pxy is false. So how do we sort of make sense of this information here? Well, if pxy is true, and we know that this statement holds, in other words, we are assuming that A is true, and we know that pxy is true. What does that tell us? Well, since the implication is assumed to be true, we can conclude that pyx is true. And we have a name for this, it's called modus ponens. Right? So in the case when pxy is true and pyx is true, we can derive that pxy and pyx is true. In other words, we've shown that this guy is true. But if we show that one part of a disjunction is true, then the entire part of the disjunction is going to be true. So this tells us that pxy and pyx as a whole, I don't even care about the other guy, this will definitely be true. Right? This whole thing is definitely going to be true. And we're good to go. At least that's for the first part. Now there is a second part when pxy is false. And what does that tell us? It tells us that the negation of pxy is true. So what tricks do we have up our sleeves? Well, this weapon that we have here is very sneaky. Because it's an implication, we can actually write it in terms of its contrapositive. And I'm even going to do a little bit of sleight of hand here. Right? This would be the negation, right? Negation of the Q implies that the negation of the P. Right? This is the contrapositive, which is equivalent to the original proposition. And you notice that I swapped the x's and the y's because we could. So we can let's swap all of these x's and the y's one more time. X, y, well, this was our x, y, y, x. So if you look carefully and you trace the relationship from one to the other carefully, I pulled a sleight of hand here, and that is actually a legitimate sleight of hand. It tells us that this is true. And what it tells us is that since the negation of pxy implies the negation of pyx is true, we can conclude that the final guy has to be true. Once again by modus ponens. And this will allow us to conclude that the negation of pxy and the negation of pyx is the conjunction of two true statements. So this is going to be true. And this expression is this guy is going to be true. So when you take anything or true, the conclusion is here. The conclusion is true, right? So in either case, you've proven that if A is true, then you've concluded that B is true. So that's part one. We still need to prove a second part of our claim. So let's do that. Now instead of proving that B is true, we need to prove that A is true. We need to prove that A is true if we assume that B is true. So, how do we go about that? Well, we need to prove we have a part 2, right? The part 2 is going to be in the left direction. So now we need to suppose that B is true. Is true. What that will tell us is that well, what does B is true mean? It means that we can now use this information freely as we would like to, right? We need to prove it. So let's prove A. So we need to fix, it's a for all statement, so we need to fix X and Y in A. And once again, since Pxy is a predicate, and you plug in the X and Y's, it is a proposition, which is true or false. So let's see what we need to do. Well, technically, we have two cases, right? The first case is if Pxy is false. If Pxy is false, suppose Pxy is false, then the implication is going to be false implies anything. Once again, no one cares. It's going to be automatically true because nobody cares, right? I forgot that it's actually an implication statement. So actually, we just need to assume that Pxy is true. So now let's do that. Suppose Pxy is true. These are our two different cases we have to deal with. And if Pxy is true, well, what can we do? If Pxy is true, what's our goal? Our goal is to show that Pyx is true. That's the goal. Now, how do we go about that? Well, we know that if Pxy is true, then the negation of Pxy is false. And at this point in time, it feels like I don't really know how to proceed on in the question. But what have we not used? We actually haven't used this weapon over here. And that is that this statement is always true. This statement is true. So in other words, we know that from B, we know that this statement is true. But we do know that negation of pxy is false, which tells us that this guy is false. But if this guy is false, then this entire expression is false. So how can we get the expression to be false and yet the whole disjunction is still true? The only result we can get is that this guy has to be true. In other words, pxy and pyx is true. And I think you can argue this is the case. I think the technique is called by elimination. But if the conjunction is true, conjunction being true is a really strict condition because we must have that both of them are true. And if we know that both are true, we know that what we are looking for, this is our goal, right? We know that what we are looking for is true. So it was a rather involved proof. This is like a part 2 if you would. But there is that. But that's how we do with two-sided proofs. We go from one to the other, and then we go from the other to the back, right? We go from left to right and then right to left. That's the usual modus operandi, if you would. We have a question over here. We have another question over here, which is a claim, or rather I'll call this an inverted commas claim, that x squared minus 6x plus 7 is bigger than 0 for all real numbers. And in fact, this claim is gonna be false, right? And the reason why is I can think of a counterexample, but maybe let me highlight why I think this is false. I think we can complete the square. Right, we can complete the square. Can we complete the square? Yes, let's complete the square. So we're going to get x squared minus 6x plus 9 bigger than 2. Okay, so this is my working. This is not a proof, by the way. This is not a proof, so let me write it this way. X squared minus 6x plus 9 is bigger than 0, which means that x minus 3 all squared, well, not bigger than 0, but bigger than 2, which means that x minus 3 all squared is bigger than 2. So we can, I think the number 2, then 2 minus 3 squared is going to be 1, but that's actually not bigger than 2. So this is sort of the rough working. This is not a proof, so I need to prove it properly. Right? So let's prove it properly. Prove that this guy is actually false. Oops. So we'll first negate the statement, right? So negation is there exists x in R with the property that x squared minus 6x plus 7 is going to be less than or equals to 0. And we're going to prove that this negation is true. And we're going to choose, as per our working, x equals to 2. Then x squared minus 6x plus 7 is going to be 2 squared minus 6 times 2 plus 7. This is going to be 4 minus 12, that's negative 8, plus 7, that's negative 1, less than 0, which means that x squared minus 6x plus 7 is less than or equal to 0, which means that the negation is true, and therefore the original statement is going to be false. That's going to be the approach over here. Yeah, and any other proof probably didn't account for every single case. So that's sort of the idea over there. Now for the last one, which is the last one for the day, we'll be good to go, and we'll look at sets the next time around. We claim that for any integers m and n, suppose we can find some integer k with the property that m squared plus n squared equals to k squared. Suppose this is true. What we can conclude is that m and n, m is not odd, and n is not odd. We claim that this is true and we're gonna try to prove it. So once again, we'll fix m, n as integers. And we're gonna start with what we can assume, because it's an implication, right? So we'll start with suppose there exists some integer k with the property that m squared plus n squared equals to k squared. Our goal is to show that m is not odd and n is not odd. That's the objective. And I'm not sure how to start with this, right? Well, how do we even start? I believe there were some results that were proven before, but let's just prove it directly because we can. All right. Okay. So it's really hard to prove it directly, right? It's very hard to just immediately show that m and n are not odd. So what happens if we were to instead prove that the negation is false by contradiction? So what's my strategy? Okay, this is not gonna be what I want to do because it's really quite not obvious what I should do. But if I can consider negation, there exists m n in Z such that the negation of this is true. So in other words, P n not Q. Oh, sorry. P and the negation states that the negation of P implies Q is P and not Q, right? P and not Q. I wrote the statement wrongly. Okay. There we go. M is not odd or N is not odd, right? So yeah, P, the negation of P implies Q. Well, let's write it down here. This is P. This is Q. The negation of P implies Q is P and not Q. So we can push the negation in by De Morgan's laws. And what we have here is a statement that m is odd and n is odd. There we go. So we claim that the original statement is true. So we want to prove that the negation is false. So we're going to prove by contradiction. Our proof: suppose the negation is true. Our goal: obtain a contradiction. So we want to sort of run into a brick wall, an impossible situation, and therefore conclude that the negation must be false. So we're going to suppose negation is true, so then suppose we have is true. Now, we're not asked to prove that this thing is true. So we don't come up with the m's and the n's. We are given under the supposition that it's true, so we know that there exists m and n. We don't know what this m and n are, we just know that they exist. So then there exists m and n in integers with the property that there exists k in Z with the property that m squared plus n squared equals to k squared, and m is odd and n is odd. So that's our objective. We want to show that this is this mess of things will give us a contradiction one way or another. So what can we do? Since m is odd, m will be equal to 2a plus 1 for some integer a. Indeed, that's what it means for an integer to be odd. It is 2 times some integer plus 1. And since n is odd, similarly, n equals to 2b plus 1 for some b in the integers. So now all we need to do is to try to use this information here and derive a contradiction. So we have m and n. Let's plug them into the equation, right? Plugging in. We have that m squared plus n squared equals to k squared, but m is 2a plus 1, n is 2b plus 1, k squared. Let's do some algebra, and I think we can get something that's gonna work out for us. So let's open up by algebra. And we can actually clean some stuff up. So we have this bit over here, and what that tells us is that k squared equals to 2 times something. This tells us that k squared is even. Now, I believe in the lecture notes you might have already proven that k is even, right? But I actually haven't done anything yet. So what I would love to be true, I would love this to be true, and we will have to prove this if we need to. I would love this statement to be true. Now, why would I love this statement to be true? So here's why. If I can show that k is even, then k is equal to 2c for some integer c. If I can show that k is even. I need to do that. I haven't shown it yet. I think you guys did, but I haven't. So if I can show that that's true, that would be great. Because now I can plug some stuff in. This will allow me to plug in k to be 2c all squared, which simplifies to 4c squared. And then we can do some algebra. The 2 on the left cancels out with one of the 2's on the right. We'll get 2a squared plus 2a plus 2b squared plus 2b plus 1 equals to 2c squared. And we're going to get 2 of a squared plus a plus b squared plus b plus 1 equals to 2c squared. We're going to get an odd number being equal to an even number. But that's not possible. A contradiction. So, if we can show that k is even, we are good to go. I believe it's done in the notes, but it's okay. Let's just do it. So now we're gonna claim. Yes, I'm gonna claim from scratch because we have to do this. That if k squared is even, and let's be more precise here. For any integer k, if k squared is even, then k is even. And how are we going to prove it? We'll fix k in z, and we'll suppose k squared is even. Our goal is that k is even. That's our goal. Well, it's very hard to start. I mean, how am I supposed to work with k squared? It's very hard to even do factorizations and not avoid weird square roots and whatnot. So why not, for a contradiction, suppose k is odd. let's try to derive a contradiction. Goal. Derive contradiction. And why do we derive contradiction? So that the bigger goal will be true. Because if we can show that this k being not even gives a contradiction, we can only conclude that k must be even. So let's suppose that k is odd, then k equals to 2d plus 1 for some integer d. But that tells us that k squared equals to 2d plus 1 squared. We can do some algebra there. And we can do a little bit more simplifications. And here we have k squared being 2 times something plus 1. And therefore, k squared is odd. But we've already assumed from the beginning, from the get-go, but k squared is even, which is not odd, a contradiction. And since we managed to derive our contradiction, we managed to derive that k is even. And since we managed to derive that k is even, we can apply this argument in our proof. And since we can apply this argument in our proof, we can derive an odd number being equal to an even number, which is a contradiction. Now, what did we contradict? We contradict the case that the negation is true. So since we have a contradiction, the negation is false, which means that the original is true. And that is how we do it. So that's on predicates and proofs, and the rest of discrete math is full of predicates and full of proofs. I think everyone felt a little bit of that. And if you're doing discrete math for the first time, welcome aboard. It's going to be an interesting journey, and we will be looking at some of the most key elements of discrete math in the coming days. On Monday, we're going to be doing sets, so stay tuned for that. Alright, that's that. See you guys next time.